Now that we've learned how to define the rate law, basically in terms of the rate of disappearance of reactants, it's time to use that rate law now to learn something about how those reactants change over time. How does their concentration decrease over time? And that's going to be the subject of this lesson. So our learning goals are going to be how we can monitor the progress of a reaction as a function of time. In other words, how do we develop the sort of graph that we showed at the very beginning of the last lesson? That is, it shows how the reactant or the product changes as a function of time. And then we're going to use that as a way of getting to the meaning of a reaction half-life. And the concept of half-life is going to be one that will help us understand a lot of different things, especially the half-life of first-order reactions. So let's get started. Let's suppose that you know your location, you know how fast you're moving in a particular direction. You should be able, with that information, to be able to predict where you might be in a few seconds. All right, it's a simple matter. You know where you are, you know the direction you're heading, you know how fast you're going there. Where will you be? So let's see if we can do the same kind of thing with a chemical reaction. So once again, we'll use that N2O4 to 2NO2 reaction that we've been looking at in the last lesson. And this time I'll give you a supposition for the rate law that the rate is equal to the rate constant times the concentration of N2O4. So it's a first order reaction as I've drawn it here. So the question is, if I know what the initial concentration of N2O4 is, then I should be able to use this rate law to predict the future time evolution of that concentration. So I basically have an equation for the rate that says negative the change in the concentration of N2O4 over a change in time would be equal to this rate constant times the initial concentration of N2O4. Well, that actually is a quantity that we can calculate if we have the rate constant. Now I'm going to assume that we have the rate constant for now. So the change in concentration, that is the amount of concentration that we should see alter between time 0 and a time delta t later, would be given by multiplying both sides of that rate equation by delta t, and I'm also going to move the negative sign to the other side, so that we can say that the change in the concentration of N2O4 is just negative k times the initial concentration of N2O4 times this time delta t. So we've basically taken the rate equation and unwrapped it a little bit. We've rearranged it a little bit. So now we're going to be given a direct equation that tells us how much that concentration changed. Now I'm going to note that this change in the concentration is going to be less than 0. We know that N2O4 is decreasing as this reaction proceeds, and it's going to decrease throughout the reaction. We know that this is negative because we have a minus sign in front, and we know that K is a positive number. We know that the initial concentration of N2O4 is a positive number, and the change in time is going to be defined as a positive number. So having all of that in hand, we can now write the equation of where this concentration will be at time delta t, and I'm going to designate that as the concentration of N2O4 with a subscript of delta t. That just means what is the concentration of N2O4 at time delta t after time 0. And that's just going to be equal to the initial concentration, N2O4 at time 0, plus the change in the concentration that we've just calculated, the change that was given just above there. So if I now write this out mathematically, that means that the initial concentration minus K times the initial concentration times delta T will be the new concentration at time t equals delta t. If I rearrange and group things together there, I have a very compact relationship that the new concentration of N2O4 is going to be the original concentration of N2O4 times 1 minus K delta t. All right, well, it's all fine and good to write out these mathematical equations, and maybe those make sense to you, but for many people it pays to have some kind of picture that shows us what these things look like. So let's take a look at a graph of what that equation means. So what we're drawing here is basically a picture of those equations that we were just discussing. On the upper left part of the plot shown here is the initial concentration of N2O4. It's drawn here as a black dot. Now the slope that's indicated from that line is the delta N2O4 that we calculated on the previous slide from the rate law. So that slope is telling us what direction we're going. We're going down, and it tells us how fast we're moving in that direction per unit time. So instead of delta t, I've called that first time point t1, but you can think of the difference between t1 and 0 as the same as delta t if you wish. So if I'm sitting on the black dot and I know which direction I'm moving and I'm knowing how fast I'm going there, I can predict where I will be at time t1. That's the red dot that's marked by a concentration of N2O4 with the subscript of 1. So in effect, what I've done is I've just approximated the time evolution of my concentration of N2O4 as a function of time. Now suppose I'm starting at N2O4 at time 1 and I want to move further in time. I want to move over to time t2. I would carry out the same process. I would calculate what the slope is of that line, which is just given by the rate equation. And from that slope, I would be able to predict how far N2O4 decreased in that next time interval. Now notice that the slope of that second time interval is different from the first time interval. Why is that? Well, in a first order reaction, the rate is proportional to the rate constant times the current concentration of the reactant material. So notice that N2O4 at time 1 is smaller than N2O4 at time 0. So if the rate is proportional to that concentration, that means the rate is going to be less at that time point t1 than it was at time point t0. So when it's less, that means it's not as steep. So that next interval, going from time t1 to t2, is going to be a more gradual slope. And we can see how that continues as we go on to time t2, t3, and so forth down the line. Each time the amount of N2O4 present is less because it's decreasing constantly. And because it's less, that means that the slope is also getting more gentle. It's becoming more gradual, becoming flatter and more horizontal. So this maps out a curve of points now that tell us how the concentration of N2O4 is going to change as a function of time. In effect, what we've done is we have now mapped out that curve that we had drawn at the very beginning of the last lesson for how N2O4 changes in time. Well, it turns out that we can do this in general for any reaction by just following those simple steps. We take, at a given time point, we take the slope of the concentration of our reactant A simply by using the rate law. The rate law tells us how to calculate that slope. We then extrapolate using that slope to a new concentration at the next time point, and I've drawn that as time t n plus 1 is equal to time t at t sub n plus delta t. And by extrapolating to that new time point, we now get a new concentration, and that's the concentration that represents that time point, and we would just repeat that. So what this process is basically the integrated rate law. It's a statement of how all of these reactants change their concentration over time. And again, if you're a math buff and you've taken calculus, essentially what we've done is we've integrated the derivative that represented the rate law, the differential rate law. All right, I'm not going to worry about integrating things. I am going to give you some of the results that are due to integration, but that's the reason for the name integrated rate law as opposed to differential rate law. So one thing you should remember, the differential rate law is telling you something about the instantaneous slope in the change of a reactant concentration. And the integrated rate law is going to give you global information about how that concentration changes as a function of time. So the integrated rate law is basically telling you the whole history of the movement of that concentration. So let's go back to that first order differential rate law, where the rate is written as k times N2O4 raised to the first power. The integrated rate law in this case, and this is now, if I had solved the thing exactly using calculus, I could integrate that rate law equation, and it would tell me what the value of the concentration of N2O4 is as a function of time. And I write that a couple of different ways. One, I can write it with time in parentheses, using sort of functional notation. Or I might also write time as a subscript, as I did on the previous slides, to indicate that it's the concentration of N2O4 at some time, t. All right, but in a first order integrated rate law, it turns out that concentration is equal to the initial concentration times this function, e raised to the power of minus kt. Okay, now if you haven't seen something like that before, I'll simply say that e is a number, it's a constant. It's 2.718, 2818, 28, and so forth. It's like the number pi. It goes on infinitely. It doesn't repeat itself. It is a mathematical constant. It's called the natural base. And in fact, it is so common in mathematics, it's so common in life, that in fact we also have a special version of the logarithm function. Instead of a logarithm base 10, this would be a logarithm that's base this number e, 2.718. And we even have a special symbol for that. We call it the natural logarithm, and we give it the symbol ln. So whenever you see this ln, it's a logarithm, and you probably have a button on your calculator that has ln for it, and that's the button that calculates the natural logarithm of a given number. All right, so a lot of explanation. There's actually, I think, some materials in the lesson that will help you learn about where E comes from and why it's so important. Okay, so but what we have here is now a function for the concentration of N2O4, a function of time. And that function of time means we can calculate what that concentration should be at any future time after the initial point. And that initial point is, of course, the prefactor for this e to the minus kt. All right, so what does this function look like? Well, unsurprisingly, it's a decaying function, just like the one we started to draw out on the last slide, but instead of having little discrete points, it's a continuous curve, okay, because this is a continuous function. Now, some things that I want you to note about this: the concentration A sub 0 indicates the starting point. That is the point at t equals 0. It is that first point on the left side at the top of this graph. Now the rate constant k is actually a constant that determines how fast this function goes to 0. You'll see that it's decaying down in a very smooth fashion down to 0 as it goes to larger and larger time. When k is large, this thing decays very fast, so it would basically hug the y-axis as it goes down toward 0 and t increases. But if k is small, then this function decays much more slowly. So it would stretch out and take its own sweet time about getting down to 0. It would be a very slow process of decay. So this rate constant is actually telling us something about the speed of a reaction in a first order reaction. It's telling us something very directly about how fast a concentration is going to decay as a function of time. All right, so it's something to pay attention to. Remember, k large means fast decay. When k is small, it means slow decay. And this curve, this exponential decay curve, is something that you'll see in lots and lots of different applications in life. It's probably good to get familiar with this function because it literally shows up just about everywhere where you have a process that decays by a first order rate. So what are some examples of those? All right, there's a lot of dynamical processes that have a first order rate law. And I'll mention a few. Some of you who drink coffee in the morning, you may know that if you drink your coffee very slowly, your coffee cools off as a function of time. It turns out that the temperature of your coffee cools, and it's something called Newton's law of cooling. It cools just like e to the minus time, okay? And so it is following this exponential decay curve because it is a first order cooling process. Same is true of radioactive decay. If you have a radioactive sample that emits radiation, so it's basically decaying to a different nucleus over time, it's an unstable isotope, then that radioactive decay occurs also as a first order process, and its time profile would look like very much like the plot that we drew on the last slide. Finally, obviously, many reactions are first order reactions. It's one of the most common rate laws that one finds in reactions, certainly true for unimolecular reactions, but many different kinds of reactions show this sort of first order decay process. So it's something that shows up a lot as one encounters different sorts of problems in the science world. All right, so now that we have the integrated rate law for a first order reaction and we've seen what it looks like, it's time for us to consider another way that we measure the rate of reactions, and that is through the reaction half-life. This is defined fairly simply. It's the time that it takes for a reaction to proceed halfway. Now, one way we could measure that is if we start with a certain amount of reactant and we use up half of that reactant, it's the time it takes to get to that new halfway point. So from the integrated rate law, we can actually solve for how long that takes given the first order reaction. That's the equation that's given in red here, where we're writing the concentration of A at time t sub 1/2. T sub 1/2 represents the half-life in this case. So at that point in time, the concentration of A has to be half of its initial concentration. So that's what that first equation is depicting, that A at time t sub 1/2 is equal to 1/2 of the initial concentration. Now we know from the integrated rate law that that concentration of A is also related to the initial concentration through this function e to the minus kt, and at time t 1/2 then it's equal to A at time t 1/2. So what is the solution for this? What we want to do is solve this equation for t sub 1/2, which means undoing that exponential and rearranging things a little bit. I'm going to save you the problem of doing that and just write out what the result is. In this case, if we solve for t sub 1/2, we get log of the number 2 divided by the rate constant k. Well, log of the number 2 is just a constant. It's just a number. And when we calculate it on our calculator or somewhere else, we get 0.693, and there's more digits too, but 0.693 is enough. So the half-life is directly related to the rate constant. Now this is actually kind of an interesting result because it tells us a couple of things. One, if we know the rate constant, we automatically know the half-life right away just by this equation because we can calculate it directly. The other thing would be if for some reason we knew the half-life of a process or a reaction, we could immediately get the rate constant, again, using this simple reaction. But perhaps the most noteworthy thing about this is that the half-life does not depend on how much material we started with. In other words, it does not depend on the concentration of A, the initial concentration of A. So this is a really interesting point, and we're going to see that it has some consequences when we look at the zero order and second order rate laws. So some observations about this. One, if we have small rate constant, we've already said that this corresponds to a slower decay. It takes longer for the concentration of the reactant to go away. How does that relate to the half-life? We'll look at the equation for the half-life. T sub 1/2 is equal to 0.693 divided by K. So if K is smaller, that means T 1/2 will be larger because we're dividing a smaller number into 0.693. So if the half-life is longer, that means it takes longer to get there. That means the decay is going to be slower overall in this rate process. If K was large, then we're dividing 0.693 by a larger number. And so T sub 1/2 is going to be much smaller. That indicates that the decay is faster, as we mentioned before. So we're going to see a very rapid decay in that instance. And I've already made this point, but the half-life depends only on K, not on the initial concentration of A. And this is a characteristic only of first-order processes. We're going to see that the other processes behave a little bit differently when it comes to their half-lives. Well, here's a graph that shows us something about the half-lives of, of a reaction that is a first-order reaction. Now, on the left-hand side, I've written three equations that are all equivalent equations. I've written that K times T sub 1/2 is equal to 0.693. That's equivalent to writing that T sub 1/2 is equal to 0.693 over K. That was the equation we had on the previous slide. But you also can rearrange that to say that K is equal to 0.693 over T sub 1/2. So these are three equivalent equations, each telling us something that could be useful in terms of calculating. But now let's look at that graph and explore what that half-life means for a first-order process. So I've just redrawn the exponential decay curve that we saw was the integrated rate law for a first-order equation. But what I've drawn on this are some indications of different half-lives. So if I start at the time 0, where I've got concentration A sub 0, if I go down halfway down the axis, that's the point at which it's at its half of its original concentration. Now if I move directly horizontally out to the curve and then down, that tells me what the half-life of the reaction will be. All right, so basically the blue rectangle is showing us both half of the original concentration in its height and the length of the half-life in its width. All right, so the first half-life is nicely depicted there. But now let's suppose I'm interested in the second half-life. So I'm starting at the end point of the first half-life, which is at 1/2 A0. And now the second half-life is going to be to decay from 1/2 A0 to 1/4 A0. Remember, it's half as much available. So if I go down to the purple rectangle, that's the height of that rectangle is commensurate with 1/2 A0, and I stretch it out to the right-hand side till it hits the curve. That tells me where the second half-life is going to occur. So successive half-lives are the next half-life after. But notice that the distance between the second half-life and the first half-life is the same as the distance between the first half-life and 0. In other words, each successive half-life in a first-order decay process is the same length of time. This is not true in general for decay processes, but it is true if we have a first-order or exponential decay such as we have here. This is also drawn out for the third half-life, so 3T1/2 corresponds to a concentration moving down to 1/8 of the initial concentration. If we were to move down to 1/16 of the initial concentration, that's the green box that's showing us it goes out to 4T sub 1/2, but you can see that each of those half-lives are equally spaced in time relative to each other. This is a hallmark of first-order decay processes and actually can be used sometimes with a decay curve to determine whether or not it is in fact a first-order decay curve or not. We'll talk about that in a subsequent lesson. All right, let's now make a brief look at zero-order reactions, and we'll also take a brief look at second-order reactions. Okay, remember for a zeroth-order reaction, the rate is just the constant. Rate is equal to the rate constant, K, so it doesn't change and it's not dependent upon the concentration of our reactant. So when we try to plot out its, the change in the concentration of A is just going to be minus K times delta T. All right, it's a very simple equation. And the time evolution from our initial point to the next point would tell us that the next point will be located at our initial concentration minus KT. All right, well, that's a pretty simple equation. In fact, that is the integrated rate law for a zero-order reaction. So if we want to look at how that evolves in time, we might end up with a graph that looks something like this. Notice the difference here. It is not a gradual decay to 0. It is a direct decay to 0. It's a straight line that goes down at the slope of negative K to smaller and smaller concentrations in our reactant A. And that's characteristic of a zero-order rate process. Okay, an exponential decay is more asymptotic to 0. A zero-order rate process is a direct linear descent from the initial concentration till it reaches 0. Now, how does this affect the half-life for this type of reaction. Well, here's a picture of what the half-lives would look like, and I've graphed this in the same way that I did for the first order decay in the last graph. We go down to 1/2 of the initial concentration, that's the blue rectangle. When we stretch it out over to the curve, we come down to the horizontal axis, we can define what the half-life, the initial half-life of this reaction would be. All right, but for the next half-life, if I go down to 1/4 A0 and then stretch it over, we can see that the second half-life isn't as far from the first half-life as the first half-life was from time t0. So in other words, the half-life has gotten shorter, and this also happens with the third half-life. And this is generally true of zero-order reactions, that each successive half-life is shorter than the previous one. So it accelerates in some sense, going down to half of its previous concentration. All right, this is a characteristic of zero-order reactions. One way you can think of it is first-order reactions, the half-life stays constant. For zero-order reactions, it gets less. It gets smaller with each successive half-life. All right, this leaves second-order reactions, and in this case, I'm not going to go through the arguments for how we get there, but when we integrate the rate law for a second-order reaction, the expression that we get is that 1 over the reaction at time t is equal to 1 over the initial concentration of the reactant plus the rate constant times time. I realize that this is probably not intuitive at all. It comes straight out of the mathematics. It turns out that this produces a very characteristic shape for second-order reactions that looks something like the kind of shape that we got for first-order reactions. So this is what that function looks like. Now you'll see that, again, like the first-order reactions, it's a gradual approach to zero as we go to infinite time. There's a subtle difference here that I want you to be tuned to, and that is that this is a more gradual decay to zero than it was in the exponential, in the first-order rate law case. It's decaying to zero, but it's going to take a lot longer time to get there in a second-order process, generally speaking. And the best way I can say is, graph this function in Wolfram alpha or something like that, and you can see for yourself that these are going to be different. Now, one of the challenges is going to be if you were to look at the decay of a reactant over a period of time, could you tell the difference between a first and second-order rate law? Well, that's something we'll take up in the next lesson, but the answer is yes, you can. Now, how does the half-life evolve for a second-order process? Well, here's a picture of that. Okay, again, the blue rectangle takes us down to 1/2 of the initial concentration. We follow it over to the curve, and then down, we can read that the first half-life is written down there at the bottom of the blue rectangle. The second half-life, so we're going to decay even further, another half amount, goes down to 1/4 of the initial concentration, and that's the purple rectangle. But when we stretch it over to the curve, we see that actually it goes farther out. So the gap between the second half-life and the first half-life is bigger than the gap between the first half-life and time zero. So when we go to the third half-life, it's longer still. So what we find in a second-order process is that each successive half-life is becoming longer and longer. And that's another sign that this is taking a slower decay to zero than it does in a first-order process. So our learning goals for today were, could we monitor the progress of a reaction as a function of time? And the answer is yes, but we need the integrated rate law to do that. And then we looked at the meaning of the reaction half-life, and we saw that actually it has very different behavior depending upon the order of the reaction. If it's a first-order reaction, the half-life, the successive half-lives are all the same length. If it's a zero-order reaction, they get shorter as time goes by with each successive half-life. And if it's a second-order reaction, they get longer with each successive half-life. Thank you.